Welcome to Strength and Materials for the Plant Engineer. This is part 6 on a stress transformation example that extends the work we did in the last video on developing stress transformation equations. In the example, we're going to rotate the cut plane or the face of the stress element as shown here continuously as we change theta. So we'll start out at 0 degrees and rotate up to pi over 4, that's the same as 90, then up to 180, which is pi, and after that everything repeats. So everything happens in the first and second quadrants. To refresh you on the stress transformation equations, here they are. We're going to work with sigma x prime and tau x prime y prime. That is these stresses on this cut face, which is a function of the angle theta. As it says, you really only need to see this derivation once, and then we'll move on to the Mohr circle, which does this automatically and much more elegantly for us in the future. Here we have an arbitrary stress element. This is a case of biaxial stress, so there are stresses applied in two directions in this plane stress problem. Here we have the normal stress in the x direction as 100. That might be megapascals or psi or anything you'd like. The shear stress is 50, and the normal stress in the y direction is 50. So this is our starting point at angle 0 on this axis, and when you compute the change in the rotation, you'll get an oscillation as shown. We'll go into that more in a second. For right now, just notice that the starting point here is 50 on the shear stresses. Recall that these are the same from basic statics, and we have 100 here on the normal stress. So again, red is the normal stress plot and blue is the shearing stress. I want to point out that when you do this plot, you really only need to go 180 degrees because you can see that everything repeats after 180 degrees like we talked about. Notice that the normal stress has a maximum here and a minimum here. It's separated by pi over 2. The same is true for the shearing stress. It has a minimum here and a maximum at pi over 2 later. So the maximum stresses occur on orthogonal planes. When we're talking about normal stress, the max and min stresses are called principal stresses, and they occur on principal planes. Notice also that at this point the shear stress is 0. So on the principal planes there's no shearing stress. And finally, the shearing stress, you can see, leads, here's the minimum, it leads the normal stress by pi over 4. So that's 45 degrees. To summarize these key points, the normal stress sigma x prime has a max and min value at intervals of pi over 2. These are the principal normal stresses, and as I mentioned, they occur on the principal planes. The principal stresses are also at a location where the shearing stress is tau x prime y prime equal to 0. Shear stresses are also on the same frequency. They have a min and max separation by pi over 2, and you can see that the shearing stress leads the normal stress by pi over 4. These are important points when working with stress analysis to keep in mind. Next time we'll start our discussion of the Mohr circle, which puts all this together in a very elegant fashion. See you next time. Thank you.